So for today, I will talk about spin-resolved atomic resolution imaging and how this is applied to the design of novel kind of nanoscale magnetic materials and devices. So let me first present a brief outline of what I will talk about today. So here, first of all, I will start, of course, with a brief introduction to the experimental technique of spin-polarized scanning tunneling microscopy and spectroscopy, which we have developed over a time period of more than 30 years. And I will show you how this technique provides access to magnetic materials and phenomena down to the atomic scale. I will show you then applications, first of all, the discovery of chiral domain walls, chiral spin spirals, and individual chiral skyrmions in ultra-thin magnetic layers. And then I will show you how we can make use of this technique also to have access to fundamental magnetic interactions down to the atomic level. And with this knowledge, actually, I will show you how we can go towards design of artificial magnetic materials and even spintronic devices. So let me start now, first introducing the technique of spin-polarized scanning tunneling microscopy. Actually, this technique allows to correlate the atomic structure and the local electronic structure as conventional STM, but it also can provide information about the spin structure at ultimate spatial time and energy resolution. So the basic idea of spin-polarized STM is to use a magnetically functionalized probe tip and to measure the spin-polarized or spin-resolved tunneling current between a sharp tip and the surface. So, of course, you all know about the STM technique, which has been pioneered by Gerd Binnig and Heinrich Rohrer. It actually makes use of an atomically sharp probe tip, which you bring to a distance of about 5 angstrom to a surface, and then you can really make use of this very strong exponential distance dependence of the tunneling current flow to really get then a surface profile in atomic scale dimensions. However, as you all know, STM is not only a microscopy technique. It is also a spectroscopic tool. Why? Because you can vary the applied bias voltage between tip and sample, and you can measure the local differential tunneling conductance as a function of spatial coordinates. And this provides access, according to the famous Terse-Hammond theory, to the local electronic density of states of your sample, which is a very fundamental property, of course. So this has been applied, of course, to many kinds of sample systems in the very early days of STM, primarily to semiconductors and metals. But right in the early days of STM, and I was involved really in the very early days together discussing with Gerd Binnig and Heinrich Rohrer, there was this great question: is it possible to combine this with spin sensitivity? And of course, that was a really urgent question, especially since, you know, the STM was developed at IBM Zurich, and of course, IBM had great interest in magnetic data storage, so it was an exceptionally relevant question also for the IBM researchers. Now, of course, as you all know, spin-polarized tunneling is known since the very famous work of Julier, mid of the 70s. So in his PhD work, Julier studied basically the spin-polarized electron tunneling between 2 ferromagnetic electrodes separated by insulating layer. And he found that the tunneling current or tunneling conductance in such kind of magnetic tunnel junction actually depends on the relative alignment of the magnetization orientation of both layers. You can, of course, easily interpret this in a Stoner picture of band ferromagnetism, where you have here, say, the spin down electrons, and here the spin up electrons, and here for both electrodes 1 and 2. And if you neglect spin flip scattering in the insulating barrier, and of course later on we will consider a vacuum barrier where you will not have any spin scattering, then you can only tunnel from one particular spin species of states to, of course, the states of the same spin direction. And so you can tunnel, for instance, here in this case, from occupied spin up electron states to unoccupied spin up electron states. In this situation where we have no spin down electron states available, as you will have typically for a so-called half metallic ferromagnet, which we were using in fact for the very early experiments, then of course you do not have a contribution from the spin down electrons tunneling. Now, if you change the magnetization of your second electrode, which is this top electrode now, of course, you have a mirror symmetric situation. Now you reduce now, of course, the number of states to tunnel into for the spin up electrons. And so the tunneling current will be reduced and you get a spin sensitivity of your tunneling current flow. So this was very well known much earlier than the invention of the STM. It was my idea then in the very early days of STM, mid of the 80s, really to combine these two concepts. And that has led then to the spin-polarized STM technique. But before going to that, let me say that, of course, you cannot only consider parallel and antiparallel orientation of magnetization. Of course, you can consider a more general situation, as was considered by John Slonczewski in his work published end of the 80s. He considered the situation where you have an arbitrary angle between the magnetization directions of both ferromagnetic electrodes. And he found that you have a cosine dependence then on the angle between the two magnetization orientations, and the magnitude of the spin polarized tunneling effect is given by the spin polarizations of both electrodes. This cosine dependence was indeed confirmed for planar tunnel junctions by Miyazaki and Tetsuka in this publication. This is from their original work, where you see that the conductance, tunneling conductance indeed follows this very nice cosine dependence. Now, already 5 years earlier than this work, we published our work in the field of spin-polarized STM, where you replace basically the planar insulating barrier with a vacuum barrier, and the top electrode is basically replaced by an atomically sharp magnetic probe tip. And now let's see what will happen now if we use such a magnetic probe tip and a magnetic sample with some domain structure. Say we have here a domain with a magnetization pointing downward and here magnetization pointing upward. Now, as I said, in this situation where we have parallel alignment of magnetization orientations, we would usually expect a higher tunneling current flow than the situation of antiparallel alignment. Now, the spin-polarized STM is usually operated like the conventional STM in so-called constant current mode. That was also the first mode of operation I used in this very early work. That means that if you scan now over such a domain wall, what will happen is the tip has to get closer to the surface in order to keep the current constant. And you will get an apparent step height here. It's not a topographic step height, but it is a step height which relates on one hand to the difference now in the relative orientations of magnetizations and the spin polarizations of both electrodes. That was quantitatively derived already in this early publication. And so from measuring these step heights, you can really then extract the fundamental parameters you would like to have. And you can apply this very nicely for domain imaging at a scale which was not possible before. And one of the very early examples was the 2 monolayer iron film on a tungsten 110 substrate. Such 2 monolayers of iron on tungsten 110 are ferromagnetic and exhibit a perpendicular magnetic anisotropy. And here you can see such a constant current spin polarized STM image. It's 100 nanometers times 100 nanometers in size. Here you see these double layer iron patches and you see clearly a stripe pattern. And this stripe pattern is actually related with a domain structure in these double iron layer patches. You can draw a line section. And this is shown here, where the scale on the y-axis is given in angstroms, and here the position along the scan line here. And you see that the variations due to the spin polarized tunneling effect above the different domains is extremely small. It relates basically to apparent height changes on the order of a fraction of an angstrom. Please compare that with the monatomic step height. So in the very early days of STM, it was really a great challenge to resolve this because you need instruments with very small electronic noise and very small disturbances, say from mechanical noises and so on. So it was really a very difficult experiment, especially in the early days of STM, 30 years back in time, where you did not have even commercial electronics. You had to build everything by yourself. So the question is then, can we apply this to systems where you would have an unexpected magnetic structure? And this is already the case when you go for ultra-thin iron layers now on a differently oriented tungsten substrate, namely tungsten 001. And the surprise is that monolayers of iron on tungsten 001, in contrast to tungsten 110, are in an antiferromagnetic ground state. Actually, that was theoretically predicted by Art Freeman and his group in the United States, but was never confirmed experimentally before. Also, they could not derive the magnetic anisotropy of the system at that time. So we looked at this system, and here you can see the topographic image, STM image, of a sample where we have deposited 1.3 monolayers of iron on this tungsten 01 substrate, meaning that we have a full coverage of a monolayer, but we also have second layer iron islands. And these second layer iron islands, they are also ferromagnetic, but they exhibit an in-plane magnetization orientation in contrast to the double layer of iron on tungsten 110. We can immediately prove this by making use of a spin-polarized tip, where the magnetization is oriented here within the surface plane. And then you see basically 4 different contrast levels, which relate to the 4 possible in-plane magnetization orientation for the 4-fold symmetric system. But now if we place this kind of tip above a spot where we have a monolayer coverage, the surprise was that we only see a 1-by-1 structure, as you would see with a non-magnetic tip. It's just showing the atomic structure basically of this monolayer iron film on tungsten 01. But then if you go from this in-plane sensitive tip to an out-of-plane spin sensitive tip by making use of an externally applied magnetic field, then you see a completely different pattern. It's a C2x2 superstructure, which would correspond to an antiferromagnetic ground state. And of course, from this type of experiment, we would able to conclude immediately that we would have out-of-plane magnetic anisotropy. Now, how can you rigorously prove that this is a magnetic superstructure and not, say, a kind of surface reconstruction? So the way you can prove this is shown here. So you basically make use of an externally applied field here in the upward direction when you polarize your tip also in the upward direction, and you can do so also in the opposite direction, of course. Now, this spin polarized tunneling effect, of course, would then mean that you would be sensitive to the red spin sublattice here with such kind of tip, but to the green spin sublattice to this kind of tip. So if you look at exactly the same sample spot, and we use here an atomic scale adsorbate as a kind of registry marker between these 2 data sets obtained with these differently magnetized probe tips, we see indeed here this C2x2 superstructure, and we see that we get indeed a phase shift here when looking at these line traces. We can see this more clearly if we just calculate the difference image of these 2 data sets, and then you see very nicely this C2x2 superstructure, whereas the sum image just gives you a topography of this atomic scale defect. If that would be a structural reconstruction, it would just be the opposite. The sum image would show, of course, this superstructure more clearly, and the difference image would give you just 0, no contrast. So this is the rigorous proof that we have here for the first time observed nail order on a square lattice in atomic scale dimensions. Now, the beauty is you cannot do this only on a local scale. Of course, we took also data sets on a larger scale. For instance, images 50 × 50 nanometers in size. And then we recorded such data sets, of course, for many different images where we just have shifted the sample spot. And then we put together several of these images in this case 7 images, where you see now this C2x2 superstructure related with the antiferromagnetic lattice. It's not the atomic lattice. And we see also typically all kind of defects on the surface. We see natural defects, we see single atoms of iron clusters here, and also single atomic layers of iron islands here. And we can basically create some simulations of a flight over such a surface. And you see very nicely the spatial coherence of this antiferromagnetic lattice, though you have all kind of defects present, but these defects do not harm this coherent antiferromagnetic lattice. So in principle, you would say that scattering techniques should also be able to resolve this antiferromagnetic state. But since most of the scattering techniques had limited sensitivity at that time, this antiferromagnetic ordering, as predicted by Freeman's group, could not be confirmed before our work. And as I said, in addition, we confirmed an out-of-plane anisotropy, which was later also confirmed by ab initio calculations taking spin-orbit coupling into account. Now, let me say something about the experimental conditions. So we are using for all these experiments home-built scanning tunneling microscopes. They are developed by ourselves and built in our workshops. We operate them already at room temperature under pressure conditions down to the 10 of up minus 11 millibar. If we cool down then typically to 300 millikelvin, then of course the cryostats work as additional cryo pumps. So we get even to much better vacuum conditions so that we can really study the same surface over several weeks without getting any additional adsorbates. And moreover, we have superconducting magnet systems. For instance, in this system here, we have a single axis magnet providing a field up to 12 Tesla. We have set that up between 2002 and 2003. It's published here. And you have already seen that we need this single axis magnet to change the orientation of magnetization from, say, upward to downward. However, if we would like to look at non-collinear spin textures, and that was our interest now already for more than 20 years, this is not sufficient. You need now an experimental setup where basically you have a three-dimensional vectorial magnetic field provided by a three-axis superconducting magnet, where you can apply fields at least on the order of a Tesla or so in all three directions in space. With that kind of three-dimensional vector magnet, you would then be able to control the spin orientation at the very end of your probe tip in three-dimensional space. Why is this so important? I said that we know that the spin-polarized tunneling current scales with the cosine of the angle between the magnetization orientation in your sample and on your tip. That means basically that you measure the projection of the local surface magnetization onto the quantization axis, which is given by the spin orientation of your probe tip. Meaning that if you can control the spin orientation in three-dimensional space, you can map out any component of your surface magnetization, or on the atomic scale, any component of your magnetic moment of your system. And of course, the magnitude of effect is governed by the choice of a magnetic tip. That's the only parameter, of course, you can play with to increase the magnetic contrast for a given sample. And this is, of course, what we have been working on during the past 30 years, basically to optimize our probe tips and our setups to really make these kind of experiments happening. So this kind of three-dimensional vector magnet system allowed us really to really create some milestones in the application of spin-polarized STM to non-collinear chiral spin states. And here I have put together several examples. I will go through them. The first observation of chiral domain walls on the nanoscale, the observation of chiral spin spiral states in two-dimensional ultra-thin films, the observation of chiral spin textures in quasi one-dimensional atomic chains, the observation of magnetic Skyrmion states in ultra-thin films, the first observation of individual chiral Skyrmions, as well as the investigation of Dzerzhinsky-Maria interactions down to the single atom level. So let me go step by step. I would like to get started with the system I already introduced, namely a double layer of iron on tungsten 110. Now, in contrast to the first example I presented, I'm now going towards a stepped tungsten 110 surface, where we have used step flow growth in order to prepare nanowires here of iron attached to the step edges of the tungsten 110 surface. So these nanowires are typically 15 to 20 nanometers in width, and you can see here very small domains on the order of 15 times 20, 25 nanometers. So with other techniques, it would already be impossible to visualize it this way. Of course, as I said before, we have out-of-plane anisotropy for these double layer iron layers on tungsten 110. Here again, this is an out-of-plane spin-sensitive image where we see now this domain structure. Now, if we turn to an in-plane spin contrast image, you see now, of course, that the contrast is coming from the magnetic domain walls. And we see now alternating contrast coming from the domain walls. So if we put the two information channels together, of course, it means that we have a spiral, a kind of spiral state along these magnetic nanowires of double layer iron on tungsten 110. And that was reported basically 21 years back in time. And it was Oswald Peach who came to me and said, there is a very strange observation, namely, that these spirals always have a unique sense of rotation, no matter which stripe you are looking at, no matter which sample you prepared, always a unique sense of rotation. And immediately we could prove this rigorously by applying an out-of-plane field. Because what will happen if you apply an out-of-plane field, of course, due to the Zeeman energy, one kind of domain will shrink in size and the other one will grow in size because of preferential or non-preferential orientation of magnetization with respect to the externally applied field. So what will happen is you move pairs of domain walls together to ultimately form 360-degree walls. And this can, of course, only happen if you have always a unique sense of rotation of the domain walls. If the domain walls would have opposite sense of rotation, of course, you would annihilate the domain walls. So that was a rigorous proof given in these two publications that we have a unique sense of rotation. So the question was then, what's the reason for this unique sense of rotation? And I have to say that 21 years back in time, Dzerzhinsky-Maria interactions were not so well known to us. Of course, Dzerzhinsky-Maria interactions, of course, were discussed, of course, more in the field of bulk magnetism for crystal structures lacking inversion symmetry. But for us, really, I have to be honest, at that time, it was quite a puzzle. Of course, if you consider the Heisenberg exchange interaction, which we all know about, you have here the scalar product of spins at side I and j. You have here the exchange constants jij. You sum up, of course, over all pairs ij, and you find immediately, of course, then that, for instance, these two spin configurations would be degenerate in energy. You cannot distinguish in energy between these two configurations, which would refer to a anti-clockwise and clockwise rotated system. But of course, nowadays everybody knows, of course, that there's the Dzerzhinsky-Maria interaction, where you have here the vector product of the spins at side I and j, and then here the scalar product with a Dzerzhinsky-Maria vector here. So you have basically three vectors forming a tripod, and this defines, of course, a sense of rotation. It will either then define a right rotating or a left rotating system, depending on the sign of this d vector. And it is this interaction we all know about, which makes these two spin configurations inequivalent. And this is exactly, of course, the interpretation. And it took us quite a while, actually, to figure that out. And actually, the first publication, which really explained our experimental observations, was this one, with Jelena Vedmedenko being first author from my group. That was really the first publication where we basically interpreted our results in the correct way. Now, in the same year, actually, we also studied not only iron on tungsten, but also manganese on tungsten 110. And also For manganese monolayers on tungsten 110, you can basically observe the same kind of physics, namely the dominance of Dzerzhinsky-Maria interactions to determine the ground state of such systems. So here you see a spin-polarized STM image on a very small scale here. And if you look at this image, you see a kind of beading pattern. It becomes clear if you draw a line section here across, then you see here with black data points a typical beading pattern resulting from the superposition of two spatial frequencies. A short period here which relates to the antiferromagnetic state which we observed and reported on in 2000 in Science on a small scale. But if you go to a larger scale, you see that there's a superimposed larger wavelength with a 6 nanometer period. And so the conclusion is that the ground state is not a collinear antiferromagnetic state, but it's an antiferromagnetic spin spiral state. So that was reported in Nature in the same year. And we could show experimentally rigorously that we only could observe spiral states with a unique sense of rotation, meaning that the spirosymmetric state could never be observed. So again, Dzerzhinsky-Maria interactions determine the unique sense of rotation for these antiferromagnetic spiral states. Now, in the following, we did not only observe this kind of physics for quasi two-dimensional systems, but also for quasi one-dimensional systems. A beautiful example are biatomic iron chains on a reconstructed iridium 001 surface. So the iridium 001 surface is fourfold symmetric, but it reconstructs and reduces the symmetry from fourfold symmetric to twofold symmetric. It's a 5x1 reconstruction. That gives the possibility to create by self-assembly biatomic chains of transition metals like iron, cobalt, and so on. And the structure is basically outlined here. And when looking at such biatomic chains with spin-polarized STM, you can clearly see here periodic modulation. Again, this modulation is not the atomic period here, does not reflect the atomic periodicity, but the spiral state which we have here. And indeed, we found that we have a spiral state with an amazing small period. It's a 3 atom period of this spiral, meaning that we have a rotation of 120 degrees of a magnetic moment from one atomic side to the next. And that was confirmed by ab initio calculations by our colleagues in Jülich, Stefan Blügel and his group. They did spin spiral calculations where they basically calculate the energy of assumed spirals with a Q vector. And they looked, of course, also for counter as well as clockwise rotating spin spirals. And they looked at the contribution of the Heisenberg exchange and the diam interaction. And you can see, of course, the Heisenberg exchange would give us a minimum here at a Q equals 0. That means if we only would consider Heisenberg exchange, the prediction would be a ferromagnetic collinear state. However, if we have Dzerzhinsky-Maria interaction present, and of course you can see from these ab initio calculations that we have a quite dramatic size of the DMI. It's even larger here than the conventional Heisenberg exchange, which is amazing. So it has a deep minimum here at a Q vector, which exactly equals to the 3 atom periodicity in real space. And it gives us this deep minimum also in the total energy curve. And you see immediately, of course, that it's only the DMI, which is asymmetric with respect to 0. So it fixes rotational sense. And this was all in beautiful agreement and reported in this paper here. So that was a possibility to study also spiral states in quasi one-dimensional systems. I will come back to that topic later at the very end of my talk. But now let's come to an even more exciting topic. I started with chiral domain walls and chiral spin spirals, but then we turned to another system where we could see for the very first time the physics of magnetic skyrmionic lattices and individual skyrmions. And that is a related system to the one I just discussed, where we now put an iron layer on an iridium 111 substrate. Iridium 111 is threefold symmetric. And indeed, if we grow iron monolayers here on iridium-111. We still observe here some patches of the bare iridium, and we can resolve the atomic lattice with the STM, and we can even resolve the lattice here of the iron layer. It's also hexagonal because the iron grows pseudomorphically. And with the Fourier transform, you can rigorously prove that you have nice hexagonal symmetry here. Now, the great surprise when we did these experiments back in 2005 was when we went to a magnetic tip with out-of-plane sensitivity, that we observed now a square symmetry, which in principle is incompatible with the threefold symmetry of our structure of the iron layer. Moreover, the period which we observed was 1 nanometer. And this is also incompatible with the assumption that it would be an antiferromagnetic collinear state, or of course a ferromagnetic state. So what was that then? So immediately when you go to larger scales, you see that you can of course regain the threefold symmetry by 3 rotational domains of this square lattice, which we observe with a magnetic tip. And if you start to build up a model where you have a unit cell size of 1 nanometer squared, you come up with this kind of suggestion that you have within the unit cell basically 15 iron atoms with 8 iron atoms, say, having their magnetic moments pointing downward, and 7 iron atoms having their magnetic moment upward. We call that a mosaic structure. If you draw a line section, then you would come up with a kind of spin block model where you have ferromagnetic spin blocks here, which are antiferromagnetically coupled with respect to each other. That's a possible state, and it has been calculated also by ab initio calculations by Stefan Blügel's group. It's reported in that paper here. But Jelena Medvedenko and our group found out immediately afterwards that there is a state which has much lower energy, namely a non-collinear magnetic skyrmionic lattice. And we reported already in 2007 that this kind of state might really be the ground state for such a monolayer iron on iridium-111 system. However, as I explained before, in order to prove this rigorously, you need this 3-axis magnet system. Of course, you can say that our experiment with the single-axis magnet was compatible, but there was no proof of this structure. So only after setting up this vectorial magnet system, we could really obtain maps, 3-dimensional vectorial spin maps, showing here the in-plane magnetization distribution in a color-coded fashion, where you see here the color wheel indicating the different in-plane magnetization orientations, and the grayscale image which indicates the out-of-plane magnetization distribution. I would like to note that this is raw data, so no filtering or so has been applied. And you can basically then put these information channels together to construct a 3-dimensional vectorial spin map. And here we have overlaid some arrows to indicate the magnetic moment orientation. So at the corners of this unit cell, you have an out-of-plane magnetic moment, and then the moments turn immediately here towards in-plane due to this very strong Jarzynski-Maria interaction. And this gives the extremely small size of the skyrmionic lattice periodicity. So that was the first observation of a magnetic skyrmionic lattice for an ultra-thin film system. Of course, you know that magnetic skyrmionic lattices have been observed earlier for bulk crystals lacking inversion symmetry by Pfleidorf's group in Munich based on neutron diffraction, and by Tokura's group in Japan based on Lorentz microscopy. The difference is, however, that in bulk crystals lacking inversion symmetry, the Jarzynski-Maria interaction is typically much smaller than for these interfacial systems, where interfacial DMI is much stronger. And that leads to the extremely small periods for magnetic lattices, and then to the extremely small size, as I will show you now, for individual skyrmions. So then we went on and said, okay, if it is possible to really stabilize magnetic skyrmion lattices in ultra-thin films, why not looking for individual skyrmions? You have to tune, of course, the interfacial DMI. And the best way to do so is to introduce a second interface. So we put down an additional palladium layer on this iron layer on iridium to be able to observe individual skyrmions. And that was reported in this paper here in 2013. It was a title page of Science, where we could report for the very first time on the observation of chiral magnetic skyrmions. So you see here already beautifully individual skyrmions, and you see here spirals here in this bilayer of palladium iron on iridium-111. Let's discuss now this in more detail. Of course, the spin structure, which is expected for individual magnetic skyrmions, has been calculated by the pioneering work of Alex Bogdanov in the late 80s. And we had close interactions with him for a long time. And of course, it was also his dream to really observe basically the spin texture down to atomic level. And this we could do with a spin-polarized STM. First, with an out-of-plane spin sensitivity, you see beautifully the axisymmetric appearance now of the magnetic skyrmions being about 3 to 4 nanometers in diameter here. And when you go to an in-plane magnetic sensitive tip, of course, you see then a different contrast, because now you are sensitive to the in-plane components. And of course, with respect to the center of a skyrmion, you have here magnetization then being oriented to the left and here to the right. So you expect a different contrast with an in-plane sensitive tip. And indeed, you will then see a two-stage contrast, red and blue, on the two sides of the skyrmions with respect to the center. And you see indeed that you always have red contrast to the left and blue contrast to the right for all skyrmions, meaning you have already proven that you have a unique rotational sense. And to rigorously prove the chiral nature, of course, you can do if you reverse the out-of-plane applied field. Then you reverse not only the contrast of the ferromagnetic surrounding, but you also reverse here the contrast for the in-plane magnetization orientation within your skyrmion. That was the first rigorous proof of chiral magnetic skyrmions, even down to the single-digit nanometer length scale. And based on that, of course, we could develop new ideas for Skyrmion-based magnetic data storage and logic devices, as I will now show in the next few slides. So the very first question was it possible not only to image now skyrmions at ultimately small scales, but to manipulate them, to create them artificially, and also to delete them? And in fact, you can use the same spin-polarized STM-Tip for this kind of manipulation. Why? Because if you increase the spin current density, you can exert a considerable spin torque on your magnetic layer, which allows you to destabilize the ferromagnetic state. And you can create either stable skyrmions in a metastable ferromagnetic background, or you can create metastable skyrmions in an otherwise stable ferromagnetic background. You see that indeed this works out experimentally. This is again the palladium iron bilayer on iridium-111. Here are 4 atomic defects. Notice the extremely small scale. These atomic defects are due to exchange processes between palladium and iron atoms. We used these atomic scale defects to pin skyrmions after their creation, because individual skyrmions are quite mobile. So we have to pin them at these atomic scale defects, and we can do so. So we can create skyrmions here, as you see now as additional contrast. We can just calculate the difference image of the two data sets, and now we can beautifully reveal the magnetic state of these 4 skyrmions, which we have created. Now you see we have been using an in-plane magnetized tip. You see the typical in-plane contrast, the two-stage contrast again. You see the same sense here of rotation, meaning also the artificially created skyrmions have the same unique sense of rotation as it is expected, of course. Now you can reverse the spin current direction, and then you can delete these skyrmions one by one. And again, you can reverse the spin current direction, and you can create them again in a different sequence. So extremely well reproducible, as we showed in this paper. Now, what is the physical mechanism? We have discussed this in this paper. It's not thermal noise. It's not Joule heating from the injected electrons, but the primary mechanism is spin transfer torque. So here we plot the skyrmion creation and annihilation probability as a function of externally applied field. for the two situations where we inject spin current from the tip to the sample or from the sample to the tip. And you can notice here a shift on the magnetic field axis here for these two situations. And this is nothing else than basically a reflection of the effect of spin transfer torque, which relates to an effective field of about 100 millitesla. So we could basically make use of spin transfer torque for reproducible writing and deleting individual skyrmions. Now, this is the basis for any kind of technological applications of skyrmions, that's for sure. And we asked ourselves, is it possible not only to make use of spin transfer torque, but also making use of the electric field, which is huge. If you have an atomically sharp tip and a sample just within a distance of 5 angstrom, of course, you can immediately calculate that you have a very strong electric field, and you can determine the orientation of the electric field by the sign of the applied bias voltage. And we noticed here, for the example of a free monolayer iron film on iridium 111, that we can also write and delete skyrmions one by one. Now you might say, what is this? The skyrmions here are no longer axisymmetric. They have a kind of strange shape, banana shape. Now this is coming from the fact that if you grow free monolayers of iron on iridium 111, you create a huge uniaxial strain because of the large lattice mismatch between the iron layer and the iridium substrate. So it's this huge uniaxial strain, and we have simulated this, which distorts the skyrmions. But nevertheless, the topological charge remains the same as if you would have axisymmetric skyrmions. Now, first comes the proof of the electric field origin of the effect. So you can measure, of course, the threshold bias voltage for creating the skyrmions and for deletion as a function of tip surface separation. You see here a linear dependence, which clearly indicates that's an electric field effect, and you can determine the threshold electric fields for the writing and the deletion of skyrmions, which is on the order of 3.7, 3.8 volts per nanometer. So this is the electric field which is needed to create and delete these skyrmions. Now, the beauty is, since these skyrmions have this strange shape, you can easily align them here on tracks, and you see some close relationship with data tracks on a magnetic hard disk drive. The only difference is that these bits here have only a size of 3.5 times 2.5 nanometers. So if you calculate the areal density, it would be 1,000 times larger than for current magnetic data storage devices that was discussed here in this paper. And you see even individual dark sites. These are individual vacancies in the iron layer. So we are really down to the atomic scale. So this is one possible application of skyrmions, kind of hard disk memory devices. Of course, there was another famous proposal by Albert Ferd and co-workers in Paris immediately after our discovery that indeed individual skyrmions can exist. The Ferd group published this paper and basically proposing this Skyrmion-based racetrack memory, and also showing that this could have great advantages over domain wall-based racetracks as proposed earlier by Stuart Parkin. Now, the problem was, of course, and we have noticed that, of course, you have then to detect the passing of skyrmions, say, by some kind of tunnel junction. Now, the problem is that if you use a magnetic tunnel junction with a magnetic top layer to detect the passing of a skyrmion, then this magnetic layer creates a stray field on your magnetic storage layer. We have basically calculated this effect and found that for the magnetic layers we wanted to use, this magnetic stray field would be much too large. You basically modify your spin texture in the magnetic storage layer. So then we had to come up, that was discussed in this publication, with a solution to this problem of the Skyrmion-based racetrack. And the solution was another kind of new magnetoresistive effect, which we call the non-collinear magnetoresistance effect. What is this? Of course, you all know the tunneling magnetoresistive effect. I have introduced it based on the famous work of Chiral, mid-70s, which is also at the heart of the effect used for spin-polarized STM. You all know about the tunneling anisotropic magnetoresistance effect, which allows us, even with a non-magnetic top layer, to distinguish between magnetic layers with an out-of-plane anisotropy of an on and in-plane anisotropy, because due to spin-orbit coupling effects in the band structure, there is a modification in the local density of states to which you are sensitive to with the tunneling effect, and so you can indeed distinguish between out-of-plane and in-plane magnetized layers in this way, which we also actually did 15 years back in time based on STM. Now, what we found is that there is a new kind of magnetoresistive effect, non-collinear magnetoresistive effect, which allows us to distinguish between a collinear ferromagnetic state and a non-collinear state. And the physical mechanism here is that if you have a non-collinear spin state, you have a spin mixing effect in your electronic structure. Usually you consider, of course, a quantization axis with respect, you consider spin up and spin down states. But if you have a non-collinear spin texture, of course, spin up and spin down states would mix. This gives an effect in your even spin-averaged electronic structure, which you can probe. And so you can measure this also with a non-magnetic top layer. And that was discussed here in this paper. So what we could propose in the end is a new kind of device where we can create sequences of electrical signals. We could create then electrical induced skyrmions in a magnetic storage layer. And then, of course, we can reverse the current flow to be able to read back basically the information of the skyrmions in this storage layer fully electrically. So this is an all electric field-based Skyrmion racetrack device, which we have proposed 5 years ago in a framework of a European project related with applications and industrial use of Skyrmion-based systems. Now, you all know we don't have Skyrmion-based devices on the market yet, but Skyrmion-based MRAM storage elements will be, of course, much closer now to applications because we have MRAM technology on the market. So Skyrmion-based MRAMs will be the first applications of Skyrmions as I see it now. Now, for the last part of my talk, let me discuss, of course, that we cannot use the spin-polarized STM only on the nanometer scale. We can even look at individual atoms, magnetic atoms, and fundamental magnetic interactions on the atomic scale. This is simply because the magnetic or spin-sensitive tunneling effect is also present on the single atom level. So consider a single magnetic impurity on an otherwise non-magnetic substrate. Now we are making use of antiferromagnetic probe tips to avoid stray fields from the tip, of course. And basically it's a magnetic orientation of a front atom, which is decisive for determining the magnetic contrast. Now, what you can do is, of course, you can polarize your tip with the external field. Either you can polarize it in the downward direction or in the upward direction. Now, in downward direction here in this view graph, you would have, of course, a parallel alignment of magnetic moments. You would indeed then expect the largest spin polarized tunneling conductance. So you would measure a data point here. If you reverse then the magnetic moment orientation of this atom with a field applied in the opposite direction, then you have the end of the parallel case and the spin polarized conductance would decrease. If you apply no field, of course, you would have rapid spin fluctuations. And on the time scale of your experiment, of course, you would average out any spin polarized effect. You would just measure the conductance, which you will see for a non-spin polarized STM experiment. So in the end, you could measure some kind of magnetization curves as it would be characteristic for a paramagnetic impurity. Now let's see if that is feasible. And that was discussed here in this paper here, also title page of Science, where we looked at magnetic stripes, which were created by step flow growth of cobalt stripes attached to a platinum 111 substrate. You see in different colors, different magnetization orientations of the two different parts of a stripe. And now you can see individual cobalt atoms sitting on the platinum substrate. And the question is now, if we look to atoms pretty close to the stripe and to atoms which are more far away from such stripes. What can we measure? And now let me first discuss what we measure on these ferromagnetic cobalt stripes, because first you have to see that we can really measure something reasonable. So here is a part of this cobalt nanostripe, and here are 3 atoms close to this stripe. If we place our magnetic tip above such ferromagnetic cobalt stripe, what we can measure is a hysteresis loop, obviously, from the ferromagnetic state of this cobalt. And we can even derive for coercive fields here from these hysteresis loops. That was the first time, really, that we could measure this even down to the single atom level. And the surprise came that if we place the tip now above atoms A, B, C, you see that we also get an open hysteresis loop, which was unexpected, first of all. And you see even that the 2 branches of the hysteresis loop indicated in red and in blue are now different from the atoms A, B, and C, which are placed at different distances with respect to the cobalt stripe. Now, if you have the same sequence of the red branch and blue branch, here we basically found that this is indicative of ferromagnetic coupling, whereas if you reverse the sequence of the branches, basically this is indicative of antiferromagnetic coupling. And we could even derive the magnitude of the indirect magnetic exchange coupling, which is actually active here, which explains the open hysteresis loops, meaning that we could derive not only for 3 atoms, but for many atoms, basically the strength of the indirect magnetic exchange coupling from the atoms to the cobalt nanostripe as a function of distance of the atoms. And you clearly can see that this is a kind of oscillatory behavior. So meaning that the dipolar interaction here can never explain this data set. The dipolar interaction is much too small on the atomic level. And of course, it would not explain the sign change. The antiferromagnetic interaction would always give us an antiferromagnetic coupling. So indeed, it's the very well-known Ruderman-Kittel-Kasuya-Yoshida interaction. Of course, you all know it. We can first leave the dimensionality open. We found the best fit for an effective dimensionality of 1 because of the quasi one-dimensional nature of that stripe. And then we can extract, of course, parameters like the Fermi wave vector and, of course, therefore, the Fermi wavelength, which is 3 nanometers in this case. And so we could really demonstrate for the very first time that we are able to look at RK-KY interactions on the single atom level. But we could not only do this for atoms and cobalt nanostructures. Of course, you can also do it between individual atoms, as shown here. You change distances between atoms here, and you find, and here we have now basically magnetization curves as characteristic for individual magnetic impurities, but these magnetization curves change now as we change the distance between the atoms. And here we are in the regime, actually, where we have antiferromagnetic coupling, and you see very strange appearing magnetization curves. Now, we discussed in this paper that this is indicative of antiferromagnetic coupling. I don't have time to go into the detail. What is the way to prove this experimentally? We just look at these distances of 2 cobalt atoms and basically map out the spin-resolved signal as a function of spatial coordinate. And you see immediately, indeed, that you have an antiferromagnetically coupled pair. You have here the strong difference in spin-related signal of the 2 atoms, which are otherwise completely identical. Both are cobalt atoms sitting on the same absorption site on platinum, but this is due to the different spin orientation. Now, we found, of course, this not only for cobalt pairs, but also for iron pairs and copper. And we could also map out the distance dependence of the indirect exchange interaction for iron pairs and copper. And most importantly, that gave us a roadmap for constructing artificial nanostructures and devices, because we know then at which distances we can expect strong antiferromagnetic coupling or ferromagnetic coupling. And now it's clear what we can do. Combining all that with the technique of single atom manipulation, which was pioneered by Eigler in the early 90s, we could demonstrate that we can combine single atom manipulation with spin-sensitive imaging and spectroscopy. That was demonstrated for the first time 12 years back in time. And what you can do then is you can really construct artificial nanostructures at will. You can construct chains of iron atoms as shown here with a spacing of 1 nanometer, where we know that we are in the optimum antiferromagnetic coupling regime. And indeed, the spin resolved conductance, which is color coded, indicates here immediately to the experimentalist that we have here an antiferromagnetically coupled state. We can prove this rigorously by enhancing the applied magnetic field. So you enhance the Zeeman interaction, which would like to align all the magnetic moments now parallel to the externally applied field. So we can even determine quantitatively then the Zeeman energy scale dominates over the RKKY interaction energy scale. And then we can create ferromagnetic chains. Having that kind of possibility in the past 5 years, we could move onward and really create milestones in quantum designer physics involving atomic spin systems. I don't have time really to discuss all that, so we could create tailored nanomagnets like these antiferromagnetic rings of iron atoms here on copper substrates, also on superconducting substrates. We have created all spin atomic scale logic devices. This is the only example I would like to touch upon in the very end. We have been looking at atomic scale spin transport devices through atomically well-defined structures. And we have combined spin spiral states with superconductors to look at emergent Majorana states in atomic scale hybrid systems recently. So as I said, you can create now any kind of artificial magnetic material down to the atomic level, no matter if these are ring structures or Kagome lattices. This is an example of a Kagome lattice unit, which we have published at that time. You see that you have inequivalent atomic sides for the inner ring and the outer ring of this Kagome lattice unit. And you see, if we measure the magnetization curves here for the individual atoms, you see a drastic difference. And this difference of the magnetic field response of the inequivalent atoms gives us then this unique magnetic field response here of this Kagome lattice unit. I don't have time to discuss this in detail. Please have a look at this publication. In the end, because I'm running out of time, let me discuss ultimately this example of the first demonstration of an atomic scale spin logic device demonstrated by Alex Khachaturian, who was for 6 years postdoc in my group. Now he is full professor in Nijmegen, as you might know. So 11 years back in time, we basically demonstrated now a device as schematically indicated here, with 2 magnetic triangular islands realized by cobalt on a copper substrate, where the magnetization states are actually representing the input states of our magnetic logic device. And then we attached antiferromagnetically coupled spin chains to the corners of these triangular-shaped ferromagnetic islands. And then we basically have here center part of the device, where ultimately here we have a single atom which represents the output state of the device, which is sensitively depending on the input states. So let's call a magnetic moment orientation upward as logic 1 state and a magnetic moment orientation downward as logic 0 state, and construct this device now in the lab. This is again raw data, no filtering at all. You have here the corner of a triangular-shaped ferromagnetic cobalt island, and here we have already 2 iron atoms close to this corner. The first iron atom, as you can see from the color coding of the spin-resolved conductance signal, is antiferromagnetically coupled. We did know the distance because we measured before the distance dependence of the RKKY interaction. In the same way, we found the optimum distance for antiferromagnetic coupling of the iron atoms. So we bring here the third atom close. Okay, so you can say this has already dark contrast, low conductance. It's not surprising here that again, low conductance state is seen. Now let's bring this atom to this place and you see it change the conductance. But you might say it's not yet as bright as this atom. So the conductance is not yet as large as for that atom. Why is this? You see immediately that the distance is larger between these 2 atoms than between these atoms. So we are not yet in the optimum antiferromagnetic coupling regime as we know it from the distance dependence of the atomic scale RKKY. So we need to bring this atom a little bit closer, and you see immediately now we are in the optimum antiferromagnetic coupling regime. As an experimentalist, you can follow this distance dependence of RKKY interaction now for the very first time down to atomic level. And you can construct the device in the end. Here's the atom, which then sensitively is depending now on the input states of magnetic electrodes. We can change the magnetization in these magnetic gates, basically by an externally applied field or by local spin current injection, making again use of the spin transfer torque, as I indicated before for the Skyrmions. And if you do so, you can see now periodically the switching, and you see how the spin information is basically now transmitted along this antiferromagnetically coupled spin chain. It's a kind of spin cascading effect, and you see how the state of that atom depends now on the state of these input gates. In the end, you can, of course, realize a truth table of this logic OR gate. You see, you can look at all permutations of the states of these two magnetic islands. Here, both islands are in a bright state, meaning logic 1 state. Then also this atom here is in logic 1 state. And that's also true if we have one of the islands in a dark state. But if both islands are in a dark state, you have here also dark state. This basically is a realization now of an old spin atomic scale logic device, realizing an OR gate, and in the same work we also realized all other fundamental logic operations. Now, at the very end, just let me make clear, what I have demonstrated here for RKKY, you can also do for the Chiral-Maria interaction. We have done this for pairs of magnetic atoms now sitting on a heavy metal substrate, not on copper, but on platinum. And then you can measure the distance dependence of Chiral-Maria interactions on a single digit nanometer scale and even down to atomic. At the end, I would like to show you this. This is really at the heart of what we are doing right now. We are constructing chains now, say of iron, now on heavy metal substrates. They are again connected to ferromagnetic cobalt nanostripes to fix the moment orientation of the first iron atom. But the other moments of the other iron atoms are free, basically, to respond according to the fundamental magnetic interactions. So let's see now what the spin-polarized STM signal tells us now. You see now with the color coding that we first have a low conductance level, then a higher conductance level, a lower, then a little bit brighter, lower, but you see it's not periodic. If you draw a line section here across this one-dimensional structure, you have again a beating pattern, like for the manganese layer on tungsten 110 I discussed at the very beginning. And this beating pattern again is a result of superposition of two spatial frequencies, namely a short wavelength period resulting from a preferential antiferromagnetic alignment of spins and a superimposed longer wavelength, which is due to the interfacial DMI. And so in the end, you create now a non-collinear state. And again, you can map out by tuning the distances between the atoms, the distance dependence of the DMI in the same way as you did for the indirect magnetic exchange coupling. With these two kinds of information channels, you can construct currently any kind of non-collinear state in 1 and 2 dimensions. So you can even create artificial Skyrmions now from the bottom up. And this in the end was recently applied by our group to create artificial spin chains of iron. They are monatomic spin chains now on superconducting rhenium. That's exactly the ingredient as theorists proposed for looking at emergent Majorana states and such kind of hybrid systems. And indeed, we showed that for monatomic iron chains on rhenium, due to large interfacial DMI, we got also very short period spirals with only 4 atom periodicity, meaning we have only 90 degrees orientation between the magnetic moments of neighboring sites. And if we look at the ends of those spin chains, You can clearly see at zero bias the expected zero energy modes here related with non-trivial Majorana states, which we have reported about 4 years ago. These Majorana states were theoretically predicted to emerge at the ends of spin chains coupled to S-wave superconductors. And these Majorana bound states appear in addition to the Yusheva-Rusinov states, which always appear if magnetic impurities are interacting with superconductors. So in the end, my time is really up. Let me summarize by saying that tunneling has proven in the past 70 years to be one of the most powerful analytical tools in nanoscience and condensed matter research in general. Why is this? Because we know that tunneling is a direct probe of the squared wave functions of quantum systems. This is a direct result of the famous work of John Bardeen, published in the early 60s. We have learned that tunneling is the fundamental probe of at low energy scales for the superconducting state, going back to the famous work of Ivagieva and Brian Josephson. So this is fundamental actually for any kind of research on superconducting samples, as you know. And due to the famous work of Gerd Binnig and Heinrich Rohr, we knew, of course, that tunneling is a most powerful probe on a local scale, even on an atomic length scale. And it was shown, and that was the most fundamental aspect, I would say, of the work of Gerd Binnig and Heinrich Rohr, that atomic resolution can be combined with extremely low energy scales. And you never have that for far field techniques. If you are operating in a far field, you have to go to X-rays. You have to go to very large energies, being a million times larger than the energy scales you need to probe low energy excitations in condensed matter. So that was the major impact, of course, of this work, that we could combine atomic level studies with energy scales which are relevant, of course, for all the exciting low energy physics in condensed matter. And I've shown you in this talk that we can even combine it with a spin degree of freedom, allowing actually access to atomic scale magnetism, single spin experiment, and even spin interactions at the fundamental atomic level. More recently, I didn't have time to go into that. We have even shown, and other groups have also shown and published work in this field, you can even combine it with very high temporal resolution to have access to the intrinsic dynamics of atomic, molecular, and nanoscale systems. So in the end, I would say that, of course, this is work of a large group. I had the pleasure to work together with almost 300 bright young scientists in the past, including PhD students, postdocs, research assistants with great contributions of people like Kirsten von Bergmann, Andrei Kubecka, Elena Medmenko, Stefan Heinze, but also Alex Khachaturian, Jens Wiebe, Tore Poske, Hovon Kim, and so on. So it was really a great pleasure. And of course, we also contributed in other fields. Yeah, I would say that the work I presented today is really due to all these young researchers who were always enthusiastic and who make it nice to really work in condensed matter physics, even during these times of the pandemic. So in the end, I would like to thank you very much for your kind attention.